are familiar with line graphs and bar graphs, you may have this question in mind: what would you do if you have large data sets? Would line graph or bar graph would be sufficient to observe the data? The answer is maybe not. A histogram could be a better option. So for example, if you have a data set of the heights in inches of 100 male semi-professional soccer players, and their heights are continuous, of course, because the maximum difference between the heights is 0.5 inches. Then we need a more rigorous method to analyze this data set than just a line or a bar graph. We need to do some more work. Okay, and histogram would serve the purpose. A histogram is plotted the same way as the line or a bar graph. It has both a horizontal axis and a vertical axis. The horizontal axis is labeled with some data. For example, it could be any thing. We call it a variable. So the variable could be, for example, the distance from your home to school. And the vertical axis is some values that you observe parallel to that label. That value is called frequency or relative frequency. Most of the time we draw relative frequency in histogram, and the graph have a similar shape like a bar graph, but eventually that shape gives us some more information than a simple bar graph. It tells us about the center and the spread of the data, and the relative frequency is the frequency of an observed value of the data divided by the total number of data values in the sample. Now, there's a difference between a sample and a population. A population is the set of all possible values in a certain data set, while sample is the set of values that we are considering for our experiment. So, if we represent the frequency by f and the total number of data values in the sample as n, then Rf, the relative frequency, would be represented by f divided by n. For example, if there are 3 students in a class of 40 students, then f is 3, n is 40, so Rf would be 3 on 40, which is 0.075, or represents 7.5% of students. To construct a histogram, we decide how many bars do we need, and those bars are also called intervals. Many histograms consist of 5 to 15 bars, just for the purpose of clarity, and it should be your choice how many bars you choose. And the convenient starting point would be the lower value carried out to one more decimal place than the value with the most decimal places. So, for example, if the value with most decimal places is 6.1, then this is the smallest value. And similarly, we move on to the larger values until a certain limit that we have set for our data set. So please read this information by pausing this video and try to grasp the idea in your mind. We'll be discussing this example where the data are the heights, which is in inches to the nearest half inch, of 100 male semi-professional soccer players. And this means that the only difference between two data sets could be 0.5, nothing less, nothing more. So we can say that this data set would be a continuous data set. Next, we decide how we choose the width of each bar and the number of bars. And for that, we need to set the minimum and the maximum value of the width of the bar. Okay, now from our data set, the smallest value is 60. And we see that the number with the most decimal places has only one decimal. For example, 61.5. Okay, then we have to set our starting point considering a difference that could give us a number in 2 decimal places, as we discussed above. So out of the convenient numbers that could be 0.5, 0.05 and 0.005, we see that 0.05 is the number that, if subtracted from 60, would give us a number in 2 decimal places, 59.95. And if 0.05 is added to the maximum number, which is 74, then it gives us 74.05. So we can now easily set the width of each bar by choosing the number of bars that looks more suitable. To me, 8 number of bars would be suitable. So I calculate the width of each bar by subtracting 59.95 from 74.05, subtracting the final value from the initial value, subtracting the initial value from the final value and divided by 8. And that gives me the width of the bar as 1.76. Now we have set the width of the bar as 1.76, which can be rounded up to 2. So the boundaries will start by adding 2 to each initial point. So adding 2 to 59.95 would give us 61.95, and so on. If we keep doing that, the end point would be adding 2 to 73.95, which is 75.95. And in this way, we have constructed 8 intervals easily. Okay, now we look at the histogram and see that our intervals are taking values from 59.95 through to 75.95, and they cover all the values of the data that are given to us. Okay, now we have to look at the y-axis, and we see how should we fix the ticks on y-axis so as to cover the whole data. And we know that the y-axis is representing the relative frequency of the data. So we count the numbers between that lie in the first bar between 59.95 and 61.95. And we see, going back to our data, that the first 5 numbers from 60 to 61.5 lie in this interval. There are 5 numbers lying in the first interval between 59.95 and 61.95. So the relative frequency corresponding to this interval would be 5 out of 100, which is 0.05. And that will be the first tick along the y-axis. The second interval, 61.95 to 63.95, consists of 3 elements, 63.5 occurring 3 times. So the relative frequency of this interval would be 0.03, which is 3 out of 100. Similarly, you can observe the relative frequency of all other intervals, and you can see the longest interval starting from 65.95 and ending on 67.95 has all the numbers starting from 66 up to 67.5, and the total numbers in this interval are 40. So the relative frequency of the longest interval is 40 out of 100, which is 0.4. In this way, we can see the relative frequencies of all the numbers divided into 8 intervals. Now let's do an exercise in which we have a data set consisting of shoe sizes of 50 male students. The sizes are continuous, and we have to identify the correct histogram and calculate the width of each bar or class interval. And we are advised to choose 6 bars, which makes sense because the data starts from number 9 and ends at number 14, and 14 minus 9 is 6. So we can easily construct 6 intervals. Okay, so the starting point would be to first identify a convenient difference to adjust the starting point, because the starting from a point is 9, so we have to give a margin of a few decimal points before 9 and after 14. And as we discussed in an example, since the maximum decimal points in the given data set are given as 1 decimal point, so we have to consider a difference of 2 decimal points to approximate the starting and ending points. So we see that a convenient difference could be with 2 decimal points. as we discussed in the example, should be 0.05. Okay, in that case, the starting point must be 9 minus 0.05, and that should be 8.95. And the ending point, which is 14, must be 14 plus 0.05. Am I right here? Okay. If you have any difficulty in understanding, please go back to the example. So once we know the starting and the ending point, we can see that the width of the interval, or also called the class interval, should be the end point minus the initial point divided by the total number of intervals, which is 6, and it turns out to be 0.85, which is nearly equal to 1. Which means that we have to set the class interval as 1. And if we start from the initial point, which is 8.95, then 8.95 should be the starting point of the first interval, and adding 1 we get 9.95, and that should be the ending point of the first interval. We see that in the first histogram. So we are just identifying the intervals which are all the same in all the options. You can see that the class interval is 1, the first starting point 8.95, ending point 9.95, and then in the second interval it is starting point as 9.95 and ending point as 10.95, and then the third interval from 10.95 to 11.95, and so on. So the last point in the intervals is 14.95, which is the end point of the sixth interval. Okay. Now the next thing is to construct the intervals actually. And if we look at the data set, we see that the relative frequency of the first interval, which is between 8.95 and 9.95, will contain all the numbers that start from 9 and end at 9.5 before 10. And we see that there are 4 numbers: 9, 9, 9.5 and 9.5. Okay, so if there are 4 numbers, then 4 divided by the total number of elements in data set would be 4 over 50, which is 8 over 100, and so 0.08. Similarly, if there are 14 numbers in an interval, then the height should be 14 over 50, which is the relative frequency, which is 28 over 100 or 0.28. Okay, so in the first interval there are 4 elements, and so the height of the interval must be 0.08. And obviously the first option is not the option, because the height of the first interval is not going to 0.08. Okay, the second option also doesn't look like the right option, because the height of the first interval is close to 0.05, not to 0.1, where 0.08 is close to 1.1. Okay, third option could be an option. Fourth option could be an option. The height of the first interval is close to 0.1. And fifth option could be an option. So third, fourth and fifth options could be the possible options. So we look at the differences between these 3 options. If we look at carefully, we can readily see a very clear difference between these 3 options, the third, fourth and fifth options, and that is the height of the fifth interval. In the third option, the height of the fifth interval is nearly equal to 0.05, while in the fourth option, the height of the fifth interval is 0, which is the same in the fifth option. And the fifth option is the interval between 12.95 and 13.95, which means that will include all the numbers that start from 13. Now if we go back to the data, we see that there is no number starting from 13, right? So the height of this interval must be 0. Okay, this makes us believe that third option cannot be an option. The only options are fourth and the fifth options, where the height of the fourth interval is 0. And now we have to identify the difference between the two to find out which one is the right one. So I'm scanning between fourth and fifth options, and can you note down the difference where it occurs in the bars? I'm sure you have identified that the second bar and the fourth bar, they are different. The third bar is the same and the sixth bar is the same. So the second bar in the fourth case has a value close to 0.3, while in the fifth case it is exactly 0.3. And the fourth bar in the fourth case is close to 0.2, while in the fifth case it's exactly at 0.2. And since the fourth bar is a shorter bar, we look at this difference to find out which option is the correct option. So the fourth bar is the interval starting from 11.95 ending at 12.95, so it includes all the numbers starting from 12. So we go back to the data and start counting the numbers starting from 12. So 1, 2, 3, 4, 5, 6, 7, 8, 9. There are 9 numbers out of 50 that start from 12, and 9 out of 50 would mean 18 out of 100. So the height of this interval should be 0.18, not exactly 2, and which clearly tells us that the fourth option is the right option, because this is not exactly 0.2, it is below 0.2, while the fifth option has the height of the fourth interval exactly as 0.2. So we exclude the fifth option and fourth option is the right option, and now we see if we have made the right decision. Wow, we have made the right decision. Okay, and the next we also have to find the width of each bar or classed interval, and we need to enter that, and we obviously clearly know the width of each bar, which is 1, so we enter 1 and then we check our answer again, and this is also correct. Next topic is frequency polygons, which just look like line graphs. However, they are made by using the middle points of intervals that we use to draw bar graphs or histograms. After choosing the middle points of each interval, we start plotting the data points along y-axis, and a simple example can be seen here in example 2.10. Where we have the range of the graph from the lower bound and the upper bound, and the corresponding y-axis values are frequencies or cumulative frequencies. We can choose either of them. For large data sets we use cumulative frequencies, but here we will draw the frequency graph using just the frequencies. So we note that the first interval we have is between 49.5 and 59.5, and repeating the process of starting from an approximate difference that can be subtracted from the lower bound to allow the zero value. We start from 44.5 instead of the middle point of the first interval, and the second point will be the middle point of the first interval that starts with 49.5 and 59.5, which is 54.5. So this is the second point, and the third point will be the middle point of the second interval, 59.5 to 69.5, and its middle point would be 64.5, and so on. So we get 7 points from 44.5 to 104.5. You can verify all other middle points from the other intervals. And the corresponding data points are the frequency. Here we are taking as frequency as along the y-axis. And so we see that 44.5 was our assumed point corresponding to the 0 vertical axis, and 54.5, which is the second point, the second real value point, has the value 5 from the frequency column. And the third point, 64.5, corresponds to 10 in the frequency column, and so on. So when we join all these points, we get this graph that we call the frequency polygon. So this graph is called the frequency polygon as it joins all the frequencies. We recall to our previous exercise that we did about the shoe size, and we know that the intervals in that exercise ranged from 8.95 to 9.95 and 9.95 to 10.95, etc. So this is the frequency polygon of all the midpoints of the intervals joined with the data sets. The y-axis data sets are the same, starting from 0.08 and going up to 0.4. And we see that the midpoints of the first interval, 8.95 to 9.95, would be 9.45, which has the data set of 0.08 along the y-axis, which is the second point on the graph. The third point on the graph corresponds to the value 10.45, which is the midpoint of 9.95 and 10.95, and it corresponds to the y-axis value of 0.28, and you can see that it is that. Similarly, the third point corresponds to the midpoint of 10.95 and 11.95, which is 11.45, and that corresponds to the value 0.4. So in this way you can tally all the points to your exercise that you did before, and see how this frequency polygon is made. And these are both the graphs together in the interval form and in the frequency form, which means that we have the histogram of the data of our exercise as well as the frequency polygon together on the same graph. A time series graph is the best example of a line graph in which a data set is plotted against time elements on the x-axis, which could be days, hours, months, years, or whatever units of time they can be used. For example, in this example 2.12, we look at the data about the annual consumer price index, also called the ACP index, on monthly basis for 10 years, starting from 2003 to 2012. And all the months data is included here, and you see that the minimum amount coming is 181.7, and the maximum it is going up to 229 here in the first set of table 2.18. All of the values in the table 2.19 are falling below these two limits. So we plot the graph taking on the y-axis the range starting from 180 to 240, and on the x-axis, of course, we have the time starting from 2003 to 2012. And you can see that after applying all the data, there's a line graph that is increasing straight away, and gives us a very straight away information about the annual consumer price index over 10 years.